Okay, welcome to this next lecture on acoustics. We had arrived at these two equations. Okay, this term came from the continuity equation and this came from the Navier-Stokes momentum balance equation. Right now both have same units. Okay, I suppose you have noticed that because this Navier-Stokes has m over L square t square term. So, we put a divergence on it, it becomes m over L cube t square, whereas the continuity had this m over L cube t. So, if you take a time derivative it becomes m over L cube t square. So, both now have m over L cube t square. So, that is the reason we did that operation, differentiating one with time and one with space, both have same units. Okay, so we have come up till 7 and 8. Now let us look at this identity here. We have del dot of del t of rho u bar is equal to del dot rho del u bar by del t plus del dot u bar del rho by del t. Okay, let us call it 9. Now the LHS in equation 8, which is this term here, is this term here in equation 9. So we will replace this with this minus this. Okay, so let us do that. So I come up with equation 10, which is what? I replace this term with these two terms. Okay, so I get del dot del by del t of rho u bar minus del dot u bar del rho by del t is equal to minus del square p, that is 10. Okay, that is 10. Okay. Now this term here, okay, is the same as this term over here, because these are linear operators, they can interchange, the del dot and del t they can be interchanged. So this term is this term over here. So if I replace this term I get minus del 2 rho by del t square minus del dot u del rho into del rho by del t is equal to minus del square of p. Okay, call this 11. Now one thing I would like to do is that we dropped all sources. Okay, so if I include, or if I had not, if I had included all the sources, the dipole type and monopole type sources, included all sources, that equation would look like this. It would be nice to know, because you will have sources at some point, minus del dot u del rho by del t is equal to minus del square p minus del q by del t plus del dot of rho f. Okay, so this is one source, that's another source. This is an equation with sources. Okay, that's an equation with sources. Okay, now let's go back to 11. Okay, going back to 11, minus del 2 rho by del t square minus del dot u del rho by del t is equal to minus del square of p, number it as 11. Okay, now as we said that there is this acoustic perturbed pressure which is much smaller than the mean pressure. We said there is this perturbed density which is much smaller than mean density. Okay, so we are going to, what we are going to do is the total pressure P we represent as P0, the mean, with the perturbation. P dash is perturbation. The total density rho I represent as rho 0 plus rho dash, the perturbed density. Okay, so if I now substitute it in here, I get minus del 2 by del t square rho 0 plus rho dash minus del okay, one more thing before we start is the velocity u. Okay, there is no more mean velocity, no mean velocity. Okay, the fluid has no mean velocity, so the acoustic particle velocity u dash is that velocity. Okay, u is the acoustic particle velocity, so I will start using u dash for u. Okay, so if we now substitute it back into 11, I get minus del 2, or I'll change the sign, all of them are negative, del 2 by del t square rho 0 plus rho dash minus, this looks like v. Okay, del dot u dash del by del t of rho 0 plus rho dash is equal to minus del square p0 plus p dash, small p dash. Okay, so now this goes away, mean density goes away, the mean density goes away, and what we are left with over here is del 2 rho dash by del t square plus del dot u dash del rho dash by del t is equal to minus del square of p dash. Okay, now we'll further do a magnitude analysis on this. So let's see what we have is, I told you that time derivative brings a time scale in the denominator. Okay, space derivative brings a length scale in the denominator. So what I get is rho dash by t square, okay, plus u dash over L rho dash over t is equal to p dash over L square. This should be a plus. this should be a plus, this should be a plus. Okay. So now what do we have? We multiply by t square. Okay. If we do that, what do we get? We get rho dash plus u dash rho dash by c is equal to p dash by c square. Okay, and we know that u dash by c is much smaller than 1. We don't know anything else. Okay, so we have rho dash and we have rho dash multiplied by u dash by c. We know that this term is much smaller than this term. So what we have is rho dash is equal to p dash by c square, or p dash is equal to rho dash c square. Okay, even a simple scaling analysis has given that. Okay, this is actually true. The perturbed pressure is equal to perturbed density into speed of sound squared. It's an exact equation. Okay, so now what do we have over here? We have over here that we drop this term. Okay, so we have only, so let me take this equation. Copy. Paste. Okay, so if we convert the signs, what we have done is this term is this term, this term is this term, and this term is this term, and this is much smaller than this. So what I have is del 2 rho dash by del t square is equal to del square p dash. Okay, now so we have arrived at quite a big distance. Okay, so we now have to relate rho dash to p dash. Okay, once that is done, the whole picture is accomplished. Okay, so now let us see here. Now let's see here. Here we will need the process. Okay, the process by which the perturbed density becomes perturbed pressure, that is what we need over here. Okay, so now let's see, we have the state equation for an ideal gas, given by PV is equal to mRT. V is the total volume, V is the total mass of the gas, R is the specific gas constant. Okay. Now if we take the differential, so what I get is dP V plus P dV is equal to mR dt. Okay, so if I divide the left by PV and I divide the right by mRT, what do I get? I get dP by P plus dV by V is equal to dt by T. Okay. So from here, for a process at constant pressure, I have dV related by V by T dt. I have just this term and that term. Whereas a process at constant volume, okay, means dV is 0, I get dP is equal to P by T dt. Okay. So now if we write the differential equation for the first law, okay, for a fixed mass of a gas, okay, we have delta Q is equal to d of U plus delta W. Okay. Now we can go one or two routes. I will take a particular route here. So I am going to write first of all S the entropy as a function of pressure and volume, okay, so that I get the ds is equal to del S by del P at a constant V dP plus del S by del V P dV. And this I will write as del S by del T by del P V dP plus del S by del T del V by del T by del V P dV. Okay. Now if I separate it out, I have del S by del TV del T by del PV dP plus del S by del TP del T by del VP dV. Okay. Now here we bring in the equation of state. Okay, so that is dP by P plus dV by V is equal to dt by T, so that this del T by del P at constant V is T by P. Okay, so we get del S by del TV T by P dP, and similarly del S by del TP T by V dV. Okay, so that is equal to T del S by del T V dP by P plus T del S by del T P dV by V. Okay. Now this part is CV. Okay. can find out, and this part is Cp. So what we get now is Cv into dP by P, and this is 0. I should have mentioned this, okay, yes, that is equal to 0 because it's an isentropic process. Isentropic process. Okay, so then what I have is Cv into this term is equal to minus of Cp into this term. Okay, that's what I'm writing here, is equal to minus Cp into dV by V. Okay, that's because ds has been set to 0. Okay, then I have dP by P is equal to minus Cp by Cv dV by V. Okay, and we know that Cp by Cv is gamma, that ratio is gamma, and so what we have now, if we integrate ln of P is equal to minus gamma ln of V plus another constant ln of C0, okay, and this we write as ln of C0 by V to the power gamma, or P is equal to C0 by V to the power gamma. That implies P V to the power gamma is a constant C0. This is the isentropic process. Okay. Now we use this to get back to our acoustics now. Okay. In the acoustic wave derivation, acoustic wave equation, we are dealing with the pressure perturbation P dash on P0 and rho dash on rho 0, and therefore volume change V dash on V0. Okay. So if I use the total P here as a perturbation plus mean, okay, what I will get here is P0, P0 mean plus the acoustic perturbation P dash, which gives me the total P, and V0 plus V dash, that is equal to C0, okay, which is also equal to P0 V0 to the power gamma, the mean values. Okay. So now here there is a gamma, sorry. So now what I am going to do is I am going to take out P0 V0 to the power gamma, then I get 1 plus P dash by P0, okay, into 1 plus V dash by V0 to the power gamma, that is equal to P0 V0 to the power gamma. I cancel this, so this is equal to 1 now. Okay, so 1 plus P dash by P0, 1 plus V dash by V0 to the power gamma is equal to 1. Now for constant mass, a gas of constant mass, I have rho 0 V0 is equal to rho V, okay, or V d rho plus dV rho is equal to 0. D rho I will take it as a perturbed density, dV I will take it as a perturbed volume. Okay. So, what I have here is V rho dash plus V dash rho equal to 0, or rho dash by rho is equal to minus V dash by V, and I will make these the mean values. That means in the amplitude sense, rho dash by rho 0 is of the same order of magnitude as V dash by V 0, and hence much smaller than 1. Okay. If that is the case, then I can use an expansion over here. I can make this 1 plus P dash by P 0, and if this is a small quantity, I can make it 1 plus gamma V dash by V 0 plus higher order terms, that is equal to 1. Okay, HOT. Okay, this is an approximation. An approximation provided V dash by V 0 is a small quantity compared to 1. Okay, so I will ignore the higher order terms and expand this. So I get 1 plus P dash by P 0 plus gamma V dash by V 0 plus gamma P dash by P 0 V dash by V 0 is equal to 1. So this one cancels. This is a small term, this is a small term, this is a product of two small terms, so we ignore this in comparison, so that I have P dash by P 0 is equal to minus gamma V dash by V 0, but V dash by V 0 is minus V dash by V 0 is equal to minus rho dash by rho 0. So, this is equal to gamma rho dash by rho 0, or my P dash is equal to gamma P 0 by rho 0 into rho dash. Okay. This quantity we will call it C square, which will have units of speed squared unit. Okay, so that P dash is equal to rho dash C square. And if you recall, we left off at del 2 rho dash by del T square is equal to del square of P dash. This is where we left off in our wave equation derivation. So, if I now bring in this definition in here, I will get del square of P dash is 1 over C square del 2 P dash by del T square. So, that is the acoustic wave equation. Okay. So, now for a general gas which deviates from ideality, okay. So, if the gas is non-ideal, and we will take the hint from the fact that P dash and rho dash are directly related. Okay. So, we do an expansion, the general pressure, total pressure is mean pressure plus del P by del rho, rho minus rho 0, evaluated at the mean density and entropy, plus half del 2 P by del rho square, evaluated at rho 0 S0, rho minus rho 0 whole squared. Okay. We took this hint because we could write PV to the power gamma is a constant. Okay. Pressure and volume or pressure and density are related, can be related, okay, in an equation. So here also P is just a function of rho, that is the way we wrote it. Okay. So now we will ignore these higher order terms we ignore. Okay. So that my P minus P0 is equal to del P by del rho, rho minus rho 0, rho 0 comma S0. Okay. So now P minus P0 is P dash, the perturbed pressure, rho minus rho 0 is rho dash, the perturbed density. Okay. So then P dash is equal to del P by del rho, rho 0 S0 rho dash. Okay. So now we have something called adiabatic bulk modulus, which is rho 0 del P by del rho at rho 0 S0, that is B. So B by rho 0 is my del P by del rho at rho 0 comma S0. Okay. So that P dash is, I think the symbol is beta. So beta by rho 0 stick with B bulk modulus B by rho 0 into rho dash. Okay. So now for this general case also, now as we left out at del rho dash by del 2 rho dash by del t square is equal to del square of P dash, then we write rho dash, okay, as del 2 by del t square P dash, okay, into rho 0 by B. Okay. Then this has 1 over c square units, 1 over speed square units, and so we write this as del square P dash is equal to 1 over c square del 2 P dash by del t square. That is the acoustic wave equation. Okay. So now I will give you one more thing. The del square form, it's worth writing down somewhere. In Cartesian, rectangular Cartesian coordinates is given by del 2 del x square plus del 2 del y square plus del 2 del z square. Okay. And in cylindrical in cylindrical coordinates it's given by r, x and z, sorry, r theta and z, r theta and z, and that looks like 1 over r del del r, r del del r plus 1 over r square del 2 del theta square plus del 2 del z square, and in spherical coordinates del square r theta phi, it looks like 1 over r square del del r, r square del del r plus 1 over r square sin theta del del theta sin theta del del theta plus 1 over r square sin square theta del 2 del phi square. Okay, so I'll close the lecture here, and we'll continue with this idea in the next class. Thank you.